We are looking at a paper today titled Scaling the Horizon, Not the Parameters, Reaching Trillion-Parameter Performance with a 35B Agent.
Yeah, this one is from the Agents A1 team over at the Shanghai Artificial Intelligence Laboratory.
Right, and just to give you the core insight right up front, you do not always need a massive, 1 trillion parameter model to hit state-of-the-art performance on these really complex multi-step tasks.
Exactly. I mean, this team built Agents A1, which is just a 35 billion parameter model, and they are matching or even outright beating trillion parameter giants.
Like GPT 5.5, DeepSeek V4 Pro, Kimi K 2.6.
Yeah, all the heavyweights. And they pulled this off not by just blowing up the model size, but by scaling the agent's horizon.
Which is wild, producing reasoning trajectories that average like a staggering 45,000 tokens in length.
Right, backed by this highly specialized long horizon infrastructure and a really novel multi-teacher distillation process.
So welcome to AI Paper Slop. For everyone out there building agents or, fine-tuning models or just trying to keep up with the bleeding edge, we are unpacking the mechanics of this today.
It's a fun one.
How do you squeeze trillion parameter reasoning out of a 35 billion parameter model? Because if we start with the philosophy behind this research, it really seems like a direct reaction against this whole industry obsession with just piling on more and more parameters.
Oh, absolutely. It is a reaction to a very specific failure mode in those massive models. I mean, the standard approach right now just relies on sheer parameter count to memorize like vast amounts of knowledge.
Right.
But when you actually deploy these massive models as agents, you hit a wall. They suffer from this really short attention span when it comes to actual execution.
Yeah, they just want to spit out the answer.
Exactly. They collapse into these one-shot lookups or really short reasoning chains. If you give a standard 1 trillion parameter model a complex machine learning task, it basically just wants to output the final Python script immediately, just based entirely on its parametric memory.
It's kind of like comparing a massive supercomputer that can only run 1-second calculations to like a slightly slower laptop that can run a highly complex interconnected simulation for a week straight.
That's a great way to look at it.
Like the supercomputer might know more trivia, but the laptop actually gets the harder job done because it can, sustain the process.
And that sustained process is exactly what the Shanghai AI lab team calls scaling heterogeneous agent abilities.
Okay, unpack that a bit.
Well, if you want an AI to solve real-world ML engineering tasks or conduct actual scientific research, just shouting out the first answer that comes to mind completely fails.
Right, because science is messy.
Exactly. The agent needs to explore dead ends, recover from errors, test code, read documentation, and, synthesize information over thousands of steps.
But you cannot simply prompt a 35B model to just, think longer.
No. It will completely drift. It will start hallucinating or just getting stuck in a loop. You have to build structural guardrails.
Which brings us to the engine of this whole system. The paper introduces this underlying data structure they call the KAG, the Knowledge Action Graph.
Yes, the KG.
So break down how this actually keeps a model on track for 45,000 tokens.
Right, so the KG is fundamentally a 4-tuple data structure. It consists of C, A, O, and V.
Okay, let's take those one by one.
First is C, the corpus. This pretty much represents the external environment. So the documents, the code base, the databases the agent can actually interact with.
Got it.
Next up is A, the action space. And this dictates what the agent can actually do, like calling a Python interpreter or using a search engine, retrieving a specific file, things like that.
Okay, so that's the input and the verbs.
Right. Third is O, the observation space. When the agent takes an action, the environment pushes back. So the observation is the execution log or the search snippet or, the error traceback if something breaks.
Which happens a lot.
Exactly. And finally, you have V, the verifier set. These are the programmatic checks evaluating if the action actually moved the agent closer to the final goal.
Okay, I want to pause on this KG structure for a second because anyone working in AI is familiar with a standard knowledge graph.
Sure.
But usually those just store static facts, right? Like entity A is connected to entity B. But this KG seems entirely different. It doesn't just store the final answer, it preserves the entire process of how the answer was acquired.
Preserving the process is the whole point. And here is the crucial insight from the paper. The KG retains both the successful trajectories and the failed evidence-backed trajectories.
Wait, it saves the failures.
Yeah. Let's say the agent is writing code. It decides to import a specific data processing library. It runs the code, but the observation space returns a dependency error because, that library is deprecated.
Okay, so it hits a wall.
Right. The agent has to backtrack and try a different library.
Yeah.
In a standard setup, that failed attempt is basically just lost context. But in the KAC, that entire failure process, the action, the error observation, and the decision to backtrack is explicitly mapped as a node in the graph.
Oh, wow. Saving the failures is kind of like a scientist keeping their lab notebook with all the crossed out math and broken hypotheses rather than just reading the final published paper.
That's exactly it.
You learn the boundaries of the problem from the struggle.
It is absolutely vital for cross-step credit assignment during training. Because when the model looks at the graph later, it learns exactly why a path was abandoned based on the verifier feedback at that specific node.
It learns the mechanics of recovery. But if you are building a data set of 45,000 token trajectories, with all the failures and recoveries perfectly mapped out, I mean, doing that manually is completely impossible.
Oh, yeah. You can't have humans doing that.
So how did they automate the generation of this massive knowledge action graph?
They engineered this really clever proposer-solver-verifier game for self-play graph expansion. It's a highly constrained automated loop.
Okay, how does it work?
Well, the proposer module samples a region of the existing graph and proposes a new subtask. Then the solver takes its tools and attempts to complete it.
And then the verifier checks it.
Right, but the verifier is incredibly strict here. It does not just check if the final answer is correct. It actually checks the provenance of the answer.
The provenance, like where it came from.
Exactly. If the solver magically guessed the correct answer without consulting the required evidence in the corpus, the verifier just rejects the whole trajectory.
Oh, that is smart. It actively filters out the lazy paths where the model just gets lucky using its internal memory.
Exactly. It forces it to show its work.
No, managing a 45,000 token context window is just a logistical nightmare for any model. How does the solver actually handle all that information without, overflowing its context? The paper mentions some very specific tools built into the KGAG for this.
Yeah, they developed these specialized memory management tools, specifically write notes and read notes.
Like a scratch pad.
Pretty much.
Yeah.
When the context window inevitably fills up and needs to be compacted, the agent uses write notes to summarize its current hypotheses, the strategies that failed, and its next steps. And this notebook survives the context compaction.
Right.
So later it can just call read notes to instantly reorient itself.
It's leaving breadcrumbs for its future self.
Exactly. And beyond just notes, they introduced an analyze tool, which is super cool.
Oh, yeah, I saw that. How does that work?
Well, imagine the agent downloads a massive, 100 megabyte CSV file of climate data.
Okay.
Dumping that into the main context window would just instantly overwhelm the model.
It would just crash or forget everything.
Right. So instead, the agent calls the analyze tool to spawn an isolated subagent.
A subagent.
Yeah, the subagent spins up in its own separate context window, runs pandas queries on the CSV, finds the requested correlation, and then returns a concise, structured summary report back to the main agent.
It's literally delegating. It builds a management hierarchy inside its own thought process.
Yeah, it's pretty wild.
So we have this KCAG structure, which is brilliant. But a graph is really only a container. Let's look at the actual multi-domain data pipeline, like the domains they chose to populate these graphs with.
Right. So the researchers instantiated these KGs across 6 really diverse domains. But the 2 most intensive ones are long horizon search and machine learning engineering, or MLE.
Okay, let's start with long horizon search.
So for search, they constructed these massive wiki walks. They take a long chain of Wikipedia pages, but they mask out the key entities in the text.
Why mask them out?
It forces the model out of its comfort zone. It cannot just rely on its parametric memory to guess a historical date or a person's name. It has to actively navigate hyperlinks, read paragraphs of evidence, and logically deduce the missing information by traversing the graph.
And to stop the agent from just spamming tools, they enforce strict penalties during this search process, right?
They're very strict.
Because I was reading about the efficiency and repetition penalties. If the agent takes too many turns, it gets penalized. But the repetition penalty is just fascinating to me.
It's a really necessary guardrail.
It's essentially stopping the agent from frantically hitting refresh on the exact same Google search when it gets confused.
Yes.
Like if it queries the exact same string or reads the same URL within a sliding window, the verifier penalizes it.
Right. And that penalty forces exploration. When a naive agent fails, its instinct is to just try the exact same action again, hoping for a different result.
The definition of insanity.
Exactly. The repetition penalty breaks that loop and forces it to synthesize a completely new search strategy.
Makes sense.
Then if we look at the MLE domain, they utilize this framework called MLE Dojo. And here they create executable Kaggle-style solution trees.
Okay, so coding tasks.
Yeah. The corpus is the Kaggle competition specification in the raw data set, and the action space is writing, patching, and debugging Python code.
And the observation space in that MLE domain, that's the actual execution logs and the traceback errors from a local Python environment, right?
Correct. The agent basically builds a tree of alternative attempts. One branch of the tree might be implementing a random forest classifier. Another branch might be trying a neural network.
Okay.
And the verifier outcomes here are not based on, like, an LLM acting as a judge. They are the literal grader scores and evaluation metrics from executing the code on a holdout data set.
So it's not vibe coding. The agent is optimizing code against hard mathematical reality.
Exactly. Real scores.
This sounds incredibly rich. We have wiki walks with forced exploration and Kaggle environments with hard execution feedback. But if you take one 35 billion parameter-based model and try to train it on all this wildly diverse data simultaneously, wouldn't the reasoning patterns completely clash?
Oh, they absolutely clash.
Because the way you navigate a Wikipedia hyperlink is fundamentally different from how you debug a neural network tensor shape.
Right. If you try to mix all of this into a standard training loop, the gradients just interfere with each other, and the model's performance degrades. The researchers knew this, which is exactly why they designed a novel 3-stage training recipe.
Okay, break down the 3 stages.
Stage 1 is full domain supervised fine-tuning, or SFT, using about 100,000 trajectories.
So it's like teaching a chef how to safely hold a knife, turn on the stove, and, read a recipe card before you ask them to invent a new dish. SFT just teaches the model the basic mechanics of its environment, like how to format a tool call, how to read an observation.
Exactly. It just provides the behavioral baseline. Then, stage 2 is domain-level teacher training. So instead of training one massive generalist model, they branch out. They train specialized teacher models for each specific domain using reinforcement learning.
So specialized teachers got it.
For example, they create a teacher model that is exclusively an expert at using tools. But what really stands out in this stage is their extreme data efficiency.
How efficient?
In the RL stage for tool calling, they didn't use millions of examples. They reused just 64 extremely hard near-miss trajectories.
Wait, what? 64? How do you squeeze signal out of just 64 samples without the model just memorizing the final answer and instantly overfitting?
They used a PPO-style advantage normalization.
PDAPO.
Yeah, PPO stands for Proximal Advantage Policy Optimization. In really simple terms, instead of just rewarding the model for getting the final answer right, PAPO normalizes the advantage of a specific action against the model's own moving baseline.
Okay, I think I follow.
So it forces the model to find a slightly better path than it did on the previous epoch, over and over again on those same 64 hard problems.
So it learns the generalized mechanics of overcoming those specific bottlenecks, rather than just memorizing a static solution.
Exactly.
Okay, so after stage 2, you have these hyper-specialized teacher models, a coding expert, a search expert, a math expert. But the goal of the paper is a single 35B model. You can't deploy 6 different models.
Right, which brings us to stage 3, multi-teacher on-policy distillation, or OPD.
Okay, so combining them.
Right. They have to distill the knowledge from all these specialized teachers back into one deployable student model. And to do this, they introduce a new technique called Salient Vocabulary Alignment, or SVA.
Why couldn't they just use standard distillation?
Because standard sample token on policy distillation breaks down over long horizons.
How so?
Well, in standard OPD, the student model generates a trajectory, and at every single token, you compare it to the exact token the teacher model would have generated.
Right.
The problem is that language and reasoning are flexible. If the student model chooses a perfectly valid synonym or takes a slightly different but equally correct reasoning step, standard OPD penalizes the student heavily just because it diverged from the teacher's exact preferred token.
Oh, I see.
And over a 45,000 token trajectory, paths naturally diverge. Punishing valid alternative paths provides incredibly unstable, noisy guidance to the student.
Whoa, okay, so the paper mentions SVA uses and I'm quoting here, a truncated reverse KL divergence to fix this. In plain English, what is the math actually doing here?
Let's break it down. In standard forward KL divergence, the student is forced to match the teacher's entire probability distribution across all, say, 100,000 possible words in the vocabulary.
Even the unlikely ones.
Exactly. Even the tail end of words the teacher thinks have a 0.0001% chance of being correct. It's too rigid.
Right.
Reverse KL divergence flips this, focusing on making the student's high probability choices match the teacher's. But SVA goes even further by truncating it.
Truncating it, how?
The teacher looks at the vocabulary and selects a support set of the top K valid tokens. It chops off the entire tail of the distribution, renormalizes those few top tokens to equal 100%, and only evaluates the student against that small subset.
I see. Okay, imagine a human teacher grading a student's essay. Standard distillation is like the teacher demanding the student use one exact specific word.
Right.
Like if the teacher was thinking of the word rapid and the student writes fast, they just fail.
Exactly. It's way too strict.
But SVA is different. The teacher creates a salient vocabulary, like a basket of 5 or 10 perfectly acceptable words. Fast, rapid, quick, swift.
Yeah.
And as long as the student picks a word from the basket, they get full marks. It's like bowling with the bumpers up.
Okay.
It constrains the student's reasoning to a safe, productive path without micromanaging their exact trajectory.
The bumper analogy is perfect.
Mm-hmm.
And they combine this with hard domain routing.
Mean.
When a student is practicing a coding prompt, it is only supervised by the coding teacher's SVA basket. When it's doing a search task, only the search teacher guides it.
Oh, so it preserves the domain-specific preferences without mixing incompatible signals at the token level.
Exactly.
It is an incredibly elegant training pipeline. So we have the KG preserving the reasoning paths, we have the specialized data, and we have the SVA distillation combining it all into a single 35B model.
Yep.
Claim made. This model rivals 1 trillion parameter giants.
Yeah.
Realistically, looking at the benchmarks, how much of a fight is Agents A1 actually putting up on the leaderboards?
The benchmark numbers are where the claim is just thoroughly validated. Agents A1 goes head-to-head with 1T models like DeepSeek V4 Pro Max and Kimi K2.6.
Okay, let's hear the numbers.
On Seal 0, which is an intensely difficult benchmark for long horizon search, Agents A1 scores 56.4. The closest 1T model is at 55.0.
Wow, so it actually beat it.
Yeah. On IFBench, which tests complex instruction following, it hits 80.6. On HiPhO, for physics reasoning, 46.4. And on Frontier Science Olympiad, it hit 79.0.
Beating a 1 trillion parameter model in physics reasoning with a 35 billion parameter model is just staggering.
Across the board, a 35B model is matching or outright beating models that are geometrically larger.
But, static benchmarks only prove it can pass a test. The paper provides real-world application case studies that show what a 45,000 token horizon actually looks like in practice.
And these are the really fun parts.
Let's talk about the 12-hour optimization run.
This is where the model's endurance is really showcased. They gave Agents A1 a machine learning engineering task, right whale call detection in audio data.
Okay.
The objective was to build a highly accurate classification model. They just gave it the data and the goal and let it run autonomously for 12 hours.
12 hours without a human intervening at all. How does it not just get trapped in some endless debugging loop?
Because of the KK infrastructure.
Yeah.
It started with a very basic, naive convolutional neural network. It evaluated the results, realized they were poor, and checked its observations.
Right.
It autonomously reasoned that temporal audio data required a completely different approach. It implemented audio augmentation, tested it, and then completely refined the architecture into a Mel spectrogram CNN ensemble.
Wait, it just did all that on its own?
Yes, and it used its read notes tool to remember which architectures failed early on so it wouldn't try them again. Over those 12 hours, it took the validation area under the curve, the AUC, from a baseline of 0.58 all the way to 0.9935.
0.9935 is a gold medal level result in a Kaggle competition.
Exactly.
It engineered a professional-grade solution completely unattended. But honestly, the Earth Science closed-loop case study is arguably even crazier because of the sheer domain knowledge required.
Oh yeah, in the Earth Science case study, the agent was tasked with tracking Cyclone Nargis, which was a devastating storm from 2008, and reconstructing its evolution.
And it wasn't just given a neat CSV file, right?
No, not at all. It had to autonomously navigate the web, find the IBTR SES database, which is the global standard for best track cyclone data, extract the raw files, write scripts to clean the data, and compute derived meteorological metrics like translation speed and heading variations over time.
What blew my mind in this example was how it handled the intensity metrics. It generated diagnostic visualizations of the wind speeds, but it successfully preserved the different intensity estimate conventions between the WMO, the World Meteorological Organization, and the JTWC, the Joint Typhoon Warning Center.
That is such a critical detail because the WMO uses 10-minute sustained wind averages, while the JTWC uses 1 minute sustained wind averages.
Right.
If you conflate those two data sets, your charts are just meteorological gibberish.
Exactly.
The fact that the AI read the documentation, kept the context of those distinct standards over thousands of tokens, and mapped them correctly while processing raw database files is a massive achievement.
It formed a complete closed loop of planning, coding, execution, scientific analysis, and report generation.
Yeah, it fundamentally understood the constraints of the domain.
So for the ML engineer or the researcher listening to this right now, what is the real actionable takeaway from the Agents A1 paper?
The takeaway is that scaling sheer parameter size is not the only path, and perhaps not even the most efficient path, to high-level reasoning.
Right.
Knowledge transfer efficiency across heterogeneous domains requires really meticulous infrastructure. If you want state-of-the-art agent performance, you need a system like the knowledge action graph that preserves the explicit process of reasoning, especially the failures.
You have to learn from the mistakes.
Exactly. And you require smart, nuanced distillation techniques like Salient vocabulary alignment to transfer that long-horizon capability into a deployable model without destroying the signal.
It really is a masterclass in working smarter, not just infinitely larger. And that brings me to a final thought for you to take away from this. We talked about how Agents A1 uses those analyzed subagents during its long runs to investigate heavy data sets without bloating its main context window.
Yeah, the delegation.
Think about your own engineering workflows right now. Are you trying to force one massive model to hold everything, like every PDF, every line of documentation, every prompt instruction in a single bloated context window? Or could you be designing your architecture to delegate discrete analysis tasks to isolated subagents and just writing their summaries into a persistent memory graph?
This is the huge paradigm shift.
It is the difference between trying to hold the whole world in your head and building a system that can reliably check its own notes. Something to mull over before we jump into our next stack of research. Thanks for tuning in to AI Paper Sloth, and we'll catch you next time.